Approximations in section 9.7. So this time in the last video we had a strange factorial that was introduced, and also we were only looking at c equals 0 every time. So I think we'll address both those parts right away. And we'll learn why these are called Taylor and Maclaurin polynomials as well. So what if c wasn't 0? What if you wanted to create a polynomial approximation to a function like e to the x or any other function, and you wanted to do it at some arbitrary c, like you have a c in mind, but you don't want to be nailed down to something specific like 0 or 2. You want to be able to do it for anything you can imagine. Well, first then let's look at the nth order approximating polynomial, and it's convenient to write this like this. So you can see that this is kind of what we had last time, except instead of the minus c, we didn't have anything there. We just had a sub 0 plus a sub 1x plus a sub 2x squared, blah, blah, blah. And then we saw that there was some kind of factorial thing underneath. So first, let's just go like this. That's just like what we had in power series, right? Same kind of thing that we had in power series that had to do with interval of convergence. So first, let's just think of the polynomial like that. Now, let's take its derivatives and see what happens. So if we take the first derivative of that polynomial, what's going to happen? So the first term is going to drop out, that's why it's gone. Second term is just going to be, it's just a1x, remember c is a constant, so that's why it's just a sub 1. This one you're going to bring down to 2, so you have 2a sub 2, and then x minus 1 to c to the 1 power, and vice versa. So then you're going to have 3a sub 3, blah, blah, blah. Okay, and then let's take a second derivative. So now we take the second derivative, so take the derivative of this, and here's what you get. I'll let you verify that if you like. And then take the third derivative, and so on and so forth. You can see, even by the third derivative, that you have like a 2 times 3 times 1. Haha. And then if you go out to the nth term, you can see that you've got some kind of factorial animal coming in at that spot. So the idea is that factorial from our previous example, it came from this. So let's try to be a little more specific than that. Anyway, so the first fact, if you plug in x equals c, then the first polynomial with c in it, you can see that all these terms are going to go away and you're just going to get a sub 0. If you plug x equals c into the derivative, all the terms are going to go away from here on out except for the first one. That's why you get a sub 1. If you plug it into the second derivative, you can see that all these terms go away, so you'll get 2a sub 2, and so on and so forth. If you did that in the nth term one, everything would go away except for that very first term, which would now be n factorial times a sub n. Okay, so there's kind of where that factorial came from, but I thought it was on the bottom. Remember, well, this is kind of just some little bit of cleverness. We're going to see why it's on the bottom now. So this is key, big stuff right here. The book does not make a big enough deal about this, so I'm using red. It says, because the value of f and its n derivatives must agree with the value of p, isn't this what we spent the entire first video doing? We said, okay, first let the y values be the same. Then we said, let the first derivative values of the thing we want to approximate, f, and the polynomial we want to approximate it with some order, p sub n, we said let those values be the same. So that's what they're doing here. They're saying let f at that spot we want, c, right? C was the spot we want, wherever it is. Let that be the same as the y value of the polynomial. That's this. So that's where this came from. Let's use green now. Okay, then we said let the derivatives be the same. So take the derivative of the function at c, and let it be the same as the derivative of the polynomial at c. That's where this came from. And then let the derivative of the second derivative, that's what we did on that one that had the 2 factorial in it, c, here's where the 2 factorial came from. If you take that derivative, 2a sub 2, and set it equal to f prime of c, it's like the 2 would have been over here, so we move the 2 down to that side, okay? And 2 is really 2 factorial, so we can write it like that. And then if you see at the very end, you can move this n factorial down underneath the other side because you want the nth derivative of the function and the nth derivative of the polynomial to be the same. That's the key here, big time, to barely one line, actually, not even a whole sentence. Anyway, So now you put those guys as coefficients, and you've developed what's called a Taylor approximating polynomial. If you do it at c equals 0, so you can see this was done a long time ago. It's crazy. But if you do it at c equals 0, that specific type of Taylor polynomial is called a Maclaurin polynomial, just in case you see that language used at some point later on. Okay, so here's the actual theorem. So a Taylor polynomial centered at c looks like this. You have coefficients that start out as f, the y value, then the first derivative, the second derivative. We talked about where the factorial comes from underneath. And then you have the of the function, right, of f. So that's where these coefficients come from. They're from taking the derivative of the function at specific discrete values, which is very easy for a computer to do, and then just multiplying that by x minus c, and you get an approximation. Anyway, and we said if you do it for c equals 0, it's a Maclaurin polynomial. Okay? So what we spent our last time doing was finding a Maclaurin polynomial. We didn't really call it that yet, for e to the x, right? So we looked at like the second order case, and that's when we first got that 2 underneath that we were unsure about. If we did the third order case, we'd also have to include this term, and we could keep going and going and going all the way out to the nth term. And if we did that, we can see that e to the x, if we took a limit to infinity, e to the x would actually be equal to this polynomial. So that's what a Maclaurin series is going to be. You can see it's a series, of course, because you've got all these pluses, but that's for next week or another lesson. Right now we're just going to say approximate it by chopping it at some spot, like the third spot, and say it's approximately the same. Okay? Let's do our first example in this video, and then we'll stop so you can take a break. So it says find the 0, first, second, third, and fourth order Taylor polynomials for this new function. So we're going to show we can do it with any function, pretty much, any elementary function at least, anything you've studied. And let's pick c equals 1 for this one, so it's not just a Maclaurin polynomial. Okay? So the first step is, you know what, just take some derivatives of your function. So natural log of x, take a derivative, take another derivative, take another derivative. Start looking for patterns here. We wanted to do it we wanted fourth order eventually, so that's why we stopped at fourth order derivative. Anyway, then if you remember the theorem up here, let's go back to it. It said you had to plug in, right, f of c, f prime of c, f double prime of c, and etc. So that's why they're doing this, f of c, f prime of c, f double prime of c, and they're getting these guys right here, which are going to be the polynomial coefficients. Let's just write that. So those are going to be the coefficients for the polynomials that we construct, because it asked for several. Who knows why? If we're in the real world, we probably only care for the best one we can get, like that one. Okay, so let's go see where that's used. So those numbers are going to come up, right? So the first one is just going to be just that. So that coefficient was 0, right? It's going to be kind of hard to see between videos here. 0, haha. Go for red. And then the second one, we're going to have a 1 coefficient, right? So we'll have 0 plus, and then the 1 coefficient was 1, so that's where this came from. So this part was 0, so then that was 1 and times x minus 1, so that's why there's just a 1 there. So anyway, then the next coefficient we had was -1. So we're probably going to have this part. There it is, -1. Here's our -1. And where's that 2 coming from? Oh, remember, back from the theorem, 2 factorial on the second order approximator. And we've got x minus 1 squared. Okay, third one. So we've got what we've got here, right? This whole part's already done, and we're just adding on one more term. We've got a 3 factorial down there. Let's dissect this guy a little bit. So this guy should be over 3 factorial. And what did we have as our coefficient for that guy? 2? 2. So 2 over 3 factorial. 3 factorial is 3 times 2 times 1, so 2/6, 1/3. There, that's what that came from. Okay, and the last one, We're just interested in this part down here, right? So why is that 1/4? So let's go back. It's -6. Notice it's alternating minus, plus, minus. That's because the derivative is alternating 0, plus, minus, plus, minus. Anyway, we had -6 over 4 factorial is 24. So -6 over 24. That's why it's 1/4. Okay, so there you go. I like the comment here that says it shows f, the natural log, in all of these, and it shows the various orders of polynomials. You can see by the time you get out to P4 in the neighborhood of 1, they're pretty much identically the same. So it's a pretty good approximation at that point. We'll look at how good approximation probably in the next lesson. But one more video for this time. So have a look at that next one. Bye.